This is electric circuits course of second semester students offered in spring 2020 in the Department of Electrical Engineering, UET Lahore. And today's lecture is on Thevenin and Norton equivalent circuits. This is part 2 of my lecture on this topic. As I have already introduced what is Thevenin and Norton equivalent circuits in part 1, where I said we have 3 cases, and first case which I discussed in my previous lecture was about circuits where all sources are independent sources. I will discuss another example in it. Second case of circuits where all sources are dependent sources. And the third case is when we have both independent and dependent sources. In all 3 cases, we will see how to find Thevenin and Norton equivalent circuits. Of a given circuit. In finding Thevenin and Norton, as you know, we calculate V open circuit, and this V open circuit is the Thevenin voltage. We calculate I short circuit, and this I short circuit is Norton equivalent current, and R Thevenin, which is equal to R Norton, it can be calculated based on V open circuit and I short circuit. As I have started discussing a type of circuits where all sources are independent sources. I will continue the example in part 1 of my lecture. And the example, in this example, if you see part 1 of my lecture, we selected a circuit with all independent sources, and over here 6K and independent current source of 2 milliampere, a resistance 3 and a resistance over here 4K, and here is our load. We don't know at this stage, we don't know whether it is a single resistor or some combination of resistors, or it may be another circuit. We use A and B labels to these terminals, and the voltage over here is V, which is the load voltage, and the current which flows through the load is I. And in the previous lecture, I have discussed how to find Thevenin equivalent and Norton equivalent, and in today's discussion I will show you another aspect of the circuit in finding Thevenin and Norton equivalent. Now, we have to express the circuit this is the interface, and our circuit is shown like this. So this is our circuit, and we will find a way where we show this circuit, and pair of terminals A and B, and over here is load. What is inside this? We have seen that inside it was the Norton equivalent with the VT and RT. We also found, this is Thevenin equivalent, and we also found its Norton equivalent with Norton current and Norton resistance. Note that Norton current and Norton resistance and Thevenin resistance are same. Now in this part of the discussion, I will show you how we can represent this circuit mathematically. Mathematically means we will use V, which is, look at the circuit, this V is the voltage over here, the load voltage, and I. We will express this circuit like V is equal to Ki plus, you can say, C. How we can do this? If we see the circuit over here, we can use a number of methods. We can use node voltage method, we can use loop current method, but here I will show you a simple way. We see a voltage source, and this voltage source can be transformed into a current source due to 15 volt and 3K. This is 5 milliampere, and 3K is in parallel, so I have transformed the voltage source. And now the resistance over here, this resistance over here, I will reproduce the resistance over here. This is 6K, and the current source of 2 milliampere over here, and a resistance of 4K, and over here a resistance of 3K, pair of terminals A and B, and the current is flowing through the load, and the voltage which appears across the load is I and V as here. Now we can further simplify it. If we see these two resistors are in parallel, and considering these two current sources, we combine these two current sources and net upward. You know, we have current sources connected in parallel. So when current sources are connected in parallel, we can combine these, and it is the upward in the current in the upward direction is 5 minus 2 milliampere is 3 milliampere, and we can combine these two resistors which are in parallel. So this resistance, equivalent resistance, is 2K, and then we have 3K over here and 4K, and again this is pair of terminals A and B, and the current flowing is I, and we have used V as a voltage across our load, while I is the current flowing through the load. Now again we see that this is a current source and a parallel resistance. We can transform it into voltage source over here, as we have current of 3 milliampere and the resistance of 2K. This is 6 volt, and over here is 2K, and then 3K, and then over here 4K, and this is A and this is B, and the current flowing to the load is V and I, and the voltage across the load is V. You know, again, if we further simplify it over here, this is 6 volt, 2K plus 3K plus 4K, this is 9K, and this is pair of terminal A and B with the voltage V and with the current I flowing through the load over here. Now we can express this circuit in the form of an equation. So this is a loop over here. We start from here. Look at the last circuit. It is the writing loop equation. So here, what is the voltage drop over here, and then we go through this and we take this voltage drop as V, and then we complete the loop. Now I write the loop equation, and this is 9K, as I is the current which is flowing in this loop. 9K I is the voltage drop over here. This, look at the circuit, this is, and then here if we move along the direction of the mesh current, and we have V over here, voltage drop, and then we are here, this is equal to 6 volt, and now we can express it as V is equal to minus 9K I plus 6. Now this is an equation which represents the circuit. Note that we can apply node voltage or the mesh current analysis to the original circuit in order to express this circuit in the form of V and I over here. Now, in short circuit conditions, if we short circuit the output, look at the bottom circuit. If we short circuit the output like this, the current flowing through this shown in red is I short circuit. So from this mathematical representation of this circuit, so this is the voltage, I am talking about I. So this, the current, short circuit current, when voltage is equal to 0. Look at the circuit again. As output A and B, two terminals are short circuited, the voltage over here is equal to 0. Therefore, look at the circuit again. I'm talking about this voltage. Due to short circuit, no current flows through the load, and whole of the current flows through a 9K and the short circuit link, while this voltage becomes 0. So from the equation again, when V is equal to 0, the short circuit current is 6 over 9K, and this 6 over 9K is 2 over 3 milliampere, which is equal to 0.666 milliampere. Again, what is the voltage when current is equal to 0? Look at the circuit again. When we open circuit over here, the current becomes 0. This is open circuit condition, and the voltage under this condition is known as open circuit voltage. We have now open circuit voltage when I is equal to 0, and from this equation again, substitute I is equal to 0, and V open circuit is equal to 6 volt. This is V open circuit, and I short circuit was 2 by 3 milliampere. Now due to this equation, we can over here show that we can show the voltage on this axis, voltage and current on this axis, as voltage is in volts and current is in the present case is a milliampere. So when current is equal to 0, we are on this axis. When current is 0, we are here. And when current is 0, what is the voltage? Voltage is 6 volt. So we see over here voltage is 6 volt. This 6 volt is V open circuit, and when now the second thing over here is what is I when V is equal to 0? We are on this vertical axis, we are over here vertical axis. So what is this current? This current is 0.66 milliampere. So this is the current 0.666 milliampere, and this is I short circuit. Now if we join these 2 points, joining these 2 points, we have a straight line, and this is the equation of a straight line over here. This is the equation of a straight line, and this line is known as load line. Why load line? Because here output voltage is 6 volt, which is the open circuit voltage, and open circuit voltage means our load resistance is infinity, and the current over here, short circuit current means load resistance is 0. Now the load resistance, if we vary the load resistance from 0 to infinity, we have 2 points. These are the 2 points. So for any value of the resistance between 0 and infinity, we will have a output voltage and current combination which will lie on this load, on this line, and that is why this line is known as load line. Now next example will be on circuits. When all sources are dependent sources. Note that when all sources are dependent sources, Vt is equal to 0, because sources are dependent and there is no independent source in the circuit. Vt will be equal to 0, and In, Norton current, will also be 0, and the circuit will be represented only with the Thevenin resistance, and the Thevenin equivalent or the Norton equivalent will be RT, and we already know that the Thevenin and Norton resistances are same. Why the Thevenin voltage and Norton current will be 0, it will be explained in the following discussion, and we will have only Thevenin equivalent. I will repeat again, when all sources are dependent sources, the Thevenin equivalent and Norton equivalent both consists of only one resistance, and this resistance in case of Thevenin equivalent it is Thevenin resistance, and in case of Norton equivalent it is Norton resistance, and we know that both of these resistances are same. Now I will draw a circuit which consists of only dependent sources. I have selected a very simple circuit, and in this circuit we have a 1 kilo ohm resistance and another resistance of 1k, and from here it is 2k resistance, and these two are connected, and we have another resistance of 2k, and okay, we want to find Thevenin or Norton equivalent seen from this pair of terminals A and B, and in this circuit we have a dependent, sorry, there is a correction over here, we have a few, okay, we have a resistance here and a resistance here. This resistance is 2k and this resistance is 1k, and we have one dependent voltage source, and the voltage across this voltage source is 2Vx, and this is a voltage controlled voltage source. And what is Vx? Vx is the voltage across this 1k ohm resistance. Note that when Vx is 2 volt, the voltage across this dependent voltage source will be 4 volts. It is straightforward. And in this case, we have to do something different. This is our load over here. What do we do over here in order to find the Thevenin equivalent or Norton equivalent is that we apply a test voltage source over here. This is the test voltage source, external voltage source, and for simple calculations we use 1 volt source. Note that here we can also use a test current source, and the value of the current is 1 ampere. We use 1 volt source or 1 ampere source to simplify calculations, and then we find current over here. What is the current? So in this case, if we have a current source, we find the voltage over here. And what we are doing, we want to find the Thevenin equivalent of this circuit seen from the pair of terminals A and B. So over here we have a circuit such that here we have known voltage and we can find the current. So what will be the resistance of this circuit? Very straightforward. As the resistance is V over I, this will be equal to 1 over I. We know the voltage and we will find the current. Now in this circuit, look at the circuit again. In this circuit, we find the current. I am highlighting the current. What is this current? Note that we can apply node voltage methods. We can apply node voltage methods, or we can apply mesh current method. If we apply node voltage method, we will consider this as the ground node, and this will be, say, this is node 1 and this is node 2 and this is node 3. Note that in here V3 is already known, it is 1 volt. And what is V2? Look at the circuit diagram. V2 over here, V2 is 2Vx. Now what is Vx? Look at this resistance. This Vx is the voltage drop across this resistance. Now what is the voltage drop across this resistance? What is Vx? Look at the circuit diagram. This is this side is positive, this side is negative, and on this side we have V3. On this side we have V1. This is V1. This is node 1. This is node 2. This is node 3, and we can say that Vx is equal to V3 minus V1. We know what is V3. Therefore, this is equal to 1 minus V1. So Vx. This is very important result. And now we use as we have selected in here node voltage method, so we write equation for node 1. Writing equation for node 1 is current flowing in this direction, current flowing in this direction, and I will write this equation for you. This is V1. What is the current flowing downward? V1 minus 0 divided by 1K. What is the current flowing upward? This is what is the voltage across this resistance of 1K? This is V1 minus 1 volt. Look at the circuit diagram over here. It is V1 minus V3, and V3 is equal to 1 volt. And the equation will be V1 minus 1 divided by 1K. What is this current? This current is V1 minus, what is the voltage on this side? On the right hand side of this 2K resistance, this is 2Vx, and the resistance is 2K. And yes, we have written the equation for this node. Now, in this equation, Vx, we will substitute Vx, and substituting Vx, the only unknown in this equation is V1, and we can find V1, and here I have found V1 is equal to 4 by 7 volts. So you have to calculate it by yourself. Now, in order to make things clear, I will delete unnecessary things over here. Now look at the circuit diagram again. What is this current? What is this current? This current I. So this I is equal to current flowing through this. And what is this current? This is 1 volt divided by 2K. Current flowing in this direction plus this is equal to 1 minus 2Vx divided by 1K. And current flowing in this direction, this is equal to 1 minus, what is the voltage here? Look at the circuit diagram. 1 minus V1 divided by 1K is equal to here. Take few moments to understand this, and sorry, this was unnecessary. So in here, I is equal to, I is flowing towards the node over here. Look at the circuit diagram. I am highlighting the node. I is flowing towards it, and 1 by 2K is leaving. This current is leaving, and this current is leaving. And from here, if you calculate I, you will find that I is 15 by 14 milliampere. What is R Thevenin? R Thevenin, as it is the ratio of resistance is ratio of voltage and current. So what is the voltage? Voltage is 1 volt, and what is the current? It is 15 over 14 milliampere, and you will find that this resistance is 933.33 ohm. Therefore, both of the Thevenin and Norton equivalent of this circuit will be only resistance, one resistance, which is Norton resistance, and Thevenin resistance. Both resistances are same. Now, why V open circuit is equal to 0, why I short circuit is equal to 0? In this case, I will advise you to find V open circuit or I short circuit. I will not hesitate in showing you the circuit again and again. This is 1K, and over here is Vx, and another resistance of 2K, and voltage source over here. This is dependent voltage source, as it is depending on a voltage signal Vx. This is a voltage controlled voltage source. If we apply the method which we have been applying in circuits when we have all independent sources, where we used to calculate V open circuit and V open circuit and I short circuit in order to find R Thevenin, which is V open circuit or I short circuit. Note that we can calculate this Thevenin equivalent by removing all the sources and finding the equivalent resistance by series parallel combinations only when all the sources are independent sources. Now in this circuit, I will advise you to find VOC. What is VOC over here? In finding VOC, if we select node voltage method and we identify nodes, this is node 1, this is node 2, and this is node 3, and V3 is equal to V open circuit. If we write equation, node equations, we will see that in matrix form, we will see that we will have V1 and V2 and V3, and over here we have a matrix, some element over here, over here, over here, over here, over here, and strangely you will see that the right hand side matrix, it will consist of all 0 elements. Now if you find V1, V2 and V3 while right hand side is equal to 0, so this is whatever is the matrix over here, I'm just to save time, take its inverse and multiply by 0 over here. Whatever is this matrix, if we multiply it with a matrix of all zeros, what will be the result? 0, 0, 0. So it shows that V1 is equal to 0, V2 is equal to 0, and V3 is equal to 0. And you know, this V3 is V open circuit, which is equal to 0. Again, if you select mesh current, so this is mesh 1, say this is our mesh 2 and this is mesh 3. In writing mesh equations, you will see that in matrix form I1, I2, I3, and sorry, it is there is another matrix over here. I'm not writing mesh equations, and I assume that you should be able to write mesh equations due to lecture 1 over here. Again, if we find I1, I2 and I3 from here, which is inverse of the matrix of this matrix, inverse multiplied by 0, 0, 0, which is equal to, the product will be 0. And if we see I short circuit, in I short circuit over here, what do? We short circuit this. Look at the circuit diagram. This is I short circuit. So this I short circuit, this I short circuit over here, I think we will have another loop over here, say 4. In such a case, you will have a 4 by 4 matrix over here, and over here a 4th element. Anyway, if you write it, so I4 will be equal to 0, I1 is equal to 0, I2 is equal to 0, I3 is equal to 0, due to this, because we have all dependent sources. And this I4 is, what is I4? I4 is I short circuit, which will be 0. That's it. It means that when all the sources when all sources are dependent sources, when all sources are dependent sources, our Thevenin or Norton equivalent will be only one resistance. Thevenin resistance, you can say Thevenin or Norton because both are same. Now, it is now we select another example. And in this example, we will see that we have independent sources and we have dependent sources in a circuit. I have selected an example with a dependent current source with the independent current source. I'll show you values, and this is 4K, and this source is independent voltage source, and the resistance over here, this is 2K, and the circuit is like this. So again, we want to see the circuit, the Thevenin equivalent, which we see from this side, the Thevenin equivalent. And as usual, on this side we have load, which we don't know what is our load at this stage. This is load. Now showing you the values. This is Vx divided by 2000. This is 3 volt independent voltage source. This is independent current source of 2 milliampere, and the control variable in this dependent current source is Vx, and Vx is the voltage which appears across this 4K ohm resistance. Now we delete all unnecessary things over here, and in it we first of all we find V open circuit and I short circuit. In finding V open circuit, look at the circuit diagram. Output, this is open, pair of terminals AB open. Open means no current is flowing in this direction, and we find the voltage. What is this voltage? Look at the circuit diagram. What is the voltage over here? The voltage rise from B to node A. This is the voltage rise, which is V. Or it is the voltage drop from A to B. When we move from negative to positive side, it is the voltage rise, and when positive to negative side, it is the voltage drop. So what is the voltage? Because this side is open, we don't know, so we follow this path over here, so and we reach over here. So the voltage over here, I will write voltage is equal to voltage rise from B to A in the direction shown. This is equal to 3 volt, means 3 volt here, over here. This is voltage rise in this direction. So what is the voltage over here? What is the voltage across this? And the voltage across this in with this polarity, what is the voltage? It is the current flowing through this 2K ohm resistance, and multiplied by the resistance itself. Now over here, this is a plus 2K multiplied by the current flowing through 2K ohm resistance in upward direction. Again, I will over here to make it clear. So how we can find the current which is flowing, the current which is flowing through this 2K? We can use node analysis, we can use mesh analysis. So a mesh analysis is better over here, and there are only two meshes, and in these two meshes we see that if this is mesh 1 and this is mesh 2, you know, I2 is the current which is flowing through mesh 2, and as this independent current source is shared by mesh 2 only, therefore I2 is equal to 2 milliampere. Yes. Now look at the mesh 1. In mesh 1, what is I1? I write it over here. What is I1? I1 is Vx divided by 2K. If Vx is 2000 volts, it is 1 ampere. If Vx is 10 volt, it is 5 milliampere. Whatever is Vx, whatever is Vx means it will determine the current which is flowing through this dependent current source. So now, proceeding further, what is Vx over here? What is Vx? If we see the resistance across which Vx appears, you can easily say that Vx is resistance multiplied by current flowing through, listen carefully, current flowing through this resistance in this direction due to the polarity of Vx, current flowing through in this resistance from right to left. So what is the current flowing through this resistance right to left? Mesh current, direction of the mesh current, and direction of the mesh current too. So this is I1 minus I2. This is Vx. Finding Vx, substituting I1 and I2, and then you will see that Vx is equal to 8 volt. And now VO is equal to 3 volt. Look at the circuit diagram again. VO, this VO, sorry, I have used V. This V is equal to voltage rise from B to A is, we follow this path, it is 3 volt, which I have written over here. It is 3 volts, and plus the voltage across this in this direction, So what is the voltage? It is direction doesn't matter, but it is basically the voltage across this. If I consider this polarity of the voltage across this, so this is due to the current I1 flowing through this. So this is 3 volt plus 2K I1. So what is I1? I1 is Vx over 2K. And what is, as these are cancelled, so this is Vx. What is Vx? We have found Vx over here. So this is 11 volt. So our V open circuit is equal to 11 volt. This is important conclusion. Now I'll be using the same circuit. Now it is, we want to find I short circuit. Short circuit means short circuit these two pair of terminals and current flowing through this. This is I3. Now as you know from the previous work, we know what is I2, we know what is I1, and now because we have short circuited the outputs terminal A to terminal B, we have another mesh. This is mesh 3. We have to write equation for mesh 3. So writing equation for mesh 3 in the direction of the current flowing through flowing in the mesh 3, this will be equal to 2K I3 minus I1, and this is equal to 3. You know, if we move in this direction, in the direction of I3, this is voltage rise, and if we move in this direction, if considering the net upward current flowing through this 2K, so this is the polarity of the voltage. Note that if we have any resistance and current is flowing downward, and it is say 2 ampere and R is say 10 ohm, the polarity of the voltage will be this. The terminal at which the current enters, is positive, and over here the other side is definitely negative. So in here we see that from this we find I3, and I3, I have done it, you have to do it by yourself, and I3 is 11 by 2 milliampere, means it is 5.5 milliampere. And I3, you know, I3 is I short circuit. So we have calculated V open circuit and I short circuit. Therefore, Thevenin or Norton equivalent resistance is V open circuit divided by I short circuit, and this is 11 over 5.5 milliampere, and this is equal to 2K. 11 divided by 5.5, straightforward, this is equal to 2K. Now, what is Thevenin equivalent? In the Thevenin equivalent, what is the Thevenin voltage? VT is V open circuit, and this V open circuit is 11 volt over here, and this is 2K. This is our Thevenin equivalent. What is Norton equivalent? What is this current? I short circuit is IN, and this is 5.5 milliampere, and the Thevenin resistance will be same. This is equal to 2K. So we have discussed all three cases of circuits. When first I discussed a circuit where all sources are independent. Second, I discussed a circuit where all sources are dependent, and at the end I discussed a circuit where we have independent sources and dependent sources. We have both independent and dependent sources. There is an example in the textbook. Due to shortage of time, I will go through it quickly. We can exploit this Thevenin and Norton equivalent circuits in a very interesting application. Say we have, I am just discussing an example which is in your textbook. So we have a very simple circuit, and in this simple circuit we have only 3 resistors over here, but the load is our load is a diode. So what do we do over here? Yes, we can find the Thevenin equivalent over here. This is A and B, Thevenin equivalent seen by the diode, or we can find the Norton equivalent seen by the diode. R Norton, remember R Norton and R Thevenin both are same. So again, pair of terminals A and B over here, and the diode over here. So question is, what is the voltage across this diode and what is the current which is flowing through the diode? It is not very straightforward. So first of all, we see what is the Thevenin equivalent seen by the diode. The Thevenin equivalent seen by the diode, I hope you should be able to do it. The Thevenin equivalent seen by the diode is just two elements, and the Thevenin resistance is 60 ohm, and this is 2.5 volt. This is the Thevenin equivalent. And the diode over here, the diode, this is A and B. So what is the voltage and what is the current? In this I will show the voltage over here. I write an equation, I write a loop equation, because the diode over here, I don't know at this stage, I don't know anything about the diode, so I'll be using only voltage as symbol and the current V and I flowing through the diode and V. So I can write the equation over here, the equation, and writing this equation, this is it's a mesh equation. I start from here, 60 ohm resistance, this is 60 and I. Look at the circuit, I have used the letter symbol I. This is the voltage drop here across this resistance, and then this is V plus V, and then completing the mesh, this is voltage rise. So equation is complete, and from here I can write V is equal to minus 60 I plus 2.5 volt. I have expressed the circuit, whole circuit, including the diode, but note that for the diode I have used only the voltage across the diode with this polarity and the current in this direction only. Now plot this. If we plot this, as I have already done over here, if we plot this over here, what is V open circuit? What is V open circuit? We can find V open circuit when I is equal to 0 from the equation. This is 2.5 volt, and say this is 2.5 volt. This is V open circuit. So what is the I short circuit? When output is shorted, A terminal is connected to B terminal, voltage will be 0, and I short circuit is equal to 2.5 divided by 60. So this is 41.667 milliampere. When V is equal to 0, we are on the vertical axis, and this is 41.6667 milliampere. Note that this is the short circuit current and this is the open circuit voltage. And now we draw the load line. Joining these 2 points, we will have a load line over here. Now the application of this load line in this circuit is very interesting. Let me see the textbook over here, just few moments. What is the IV curve of the diode? Just be patient. Just be patient. I am just trying to find Okay, at present it is not available. I hope that you may have heard about APN junction diode in your college physics. If in the PN junction diodes over here for this, the VI relationship is usually like this, and on the other side it is like this. So as our load line is in the first quadrant, therefore we will be using this part of the VI characteristics of a diode, and the diode over here, I will just superimpose this on it. So it is, say it is like this. This is our diode shown, the VI characteristic of the diode shown. So when the load is nonlinear, I will delete all these things over here. This diode represented by this, note that diode is a non-linear element. So if our load is nonlinear and we know the VI characteristic of the diode, in this case shown in the green line, we superimpose the VI characteristic of our nonlinear load and the load line of the Thevenin equivalent or Norton equivalent, and the intersection of these two will determine the load voltage and it will determine the load current. Means this will determine the voltage. Look at the circuit diagram. This will determine the actual voltage across the diode, and this will determine the actual current across the diode. So I will say this is over here. This is VD, and this is ID, current flowing through the diode, and the voltage appearing across the diode. So due to time limitation, I have been a bit quick in this example, and this is the last example in the textbook where Thevenin equivalent and Norton equivalent are discussed. So this is end of part 2. So I have discussed Thevenin and Norton equivalent circuits with a few examples. And in first type of example, I selected a circuit when all sources are independent, and the second example was of a circuit when all sources are dependent, and the third example, we have both the independent and dependent sources. And the last example over here is when we have a non-linear load. This is very, very interesting conclusion of Thevenin equivalent, application of Thevenin equivalent and Norton equivalent. Okay, thank you for your patience, and I strictly advise you, while listening this lecture, I strictly advise you to take a pause when I complete one example, so that you can verify loop equations and node equations, and you yourself calculated by yourself the voltage, open circuit voltage, and the short circuit current, so that you can have hands-on experience. And I strictly advise you to go through each and every end problem. Just give a try to solve it, and then you can use your WhatsApp group in case of any difficulty in it. Okay, thank you very much.